Hi everyone, here we're going to go over the theory for the specific heat lab. So let's actually see what this represents here. So if you have a hot plate or some kind of a heat source, so that's constantly sending out some heat Q. And on top of that, let's say you put an object with a mass M, like a piece of metal. So what's going to happen is that the heat is going to get absorbed by that mass, and because of that, the temperature of this mass is going to start to rise. So let me be clear here. So you have this heat source, and let's say that you have the cylinder. The cylinder has a mass M, and it has some initial temperature T initial. And now you're going to place that cylinder onto that heat source. And now that cylinder is going to absorb some heat. And what the heat is going to do is it's going to make the mass's temperature rise to some new temperature T final. So first thing is that the heat then is going to depend, or the heat that the mass absorbs. So the heat is going to depend on a couple of things. The mass of the object, and also what the heat is going to do is it's going to change the temperature of the object. So it's going to depend on the final temperature minus the initial temperature. So that's not quite the equation yet. There's one more term, and the other term is the kind of metal. So you can have two different kinds of metals. They can be both the same size, but let's say that one of them is aluminum, and another one is going to be copper or iron, some other kind of metal. And so they're both going to absorb. Actually, let me be even more, make this even more clear. Let's say that you have two objects the same size. One of them is a metal, aluminum, and another one, let's say that it's clay. So there you can imagine that they're both going to receive the same amount of heat, but after 1 second you can imagine that the aluminum is going to feel hotter, whereas the clay is not going to feel as hot. So something else, there's another component to this equation that depends on the kind of material that you're looking at, and it's quantity that depends on the kind of material, and it affects how much heat the object can absorb. That's called the specific heat, and that's going to be this lowercase variable, lowercase c. And so this is the equation that we're going to verify, that the heat that an object absorbs depends on a couple of things. It depends on, well, let me say it another way. If an object absorbs heat, the more mass it has, the more heat it's going to need to absorb to raise its temperature. Or you can also say that the more heat an object absorbs, the bigger the temperature change is going to be. And the other factor that affects the amount of heat, how the object reacts to the amount of heat that it absorbs, is its specific heat. And this is so lowercase c here, that's the specific heat. So this is the term that you'll be calculating today, the specific heat. But you're going to do it in a special way. So what you're going to do is this. You're initially going to have some water. So for part one of today's experiment, you're going to have a tank of water. So water is going to have its own specific heat, seawater, and water is going to have some initial temperature, T initial. And you're also going to have a metal cylinder. And the metal cylinder is going to have its own specific heat, C metal, and it's going to have some initial temperature, T metal initial. And the metal is actually going to start off being hot. So you're going to actually heat up the metal to initial temperature of 100 degrees Celsius. And water, I believe, is going to be at room temperature. And then what you'll do is you're going to dunk the metal into the water. So you have your water here, and you're going to dunk the metal into the water, so you're going to put the metal inside the water. So because the metal is hotter than the water, that means that heat is going to leave the metal and it's going to go into the water. So what that means is that the temperature, um, so so the temperature of the metal is going to drop because it was hotter, and then you dunk it into something that was cooler. So the temperature of the metal is going to drop, and at the same time the water was cooler, but now heat is absorbing heat. So that means that the water temperature is going to rise. Effectively, what's going to happen, and I'll show you this in terms of a graph, because you're actually going to see this in terms of a graph. So you're going to have a graph of temperature versus time. And what you'll see is that initially the metal is going to start off at 100 degrees Celsius, and the water is going to be at, I believe, room temperature. So I'll just say 30. I'm just kind of guessing here. And as time goes by, their temperature is constant, and then you're going to dunk them. So, and then once you dunk them, what you'll find is that the metal's temperature is going to drop, and the water's temperature is going to rise. The water's temperature is going to rise, and until they both reach a common temperature, and after that, the temperature is going to stay constant at some final temperature, T final. So what that means is that when you mix the metal into the water, eventually there's going to be a point where the metal is going to give up heat, and the water is going to absorb heat until both of them are at the same common final temperature. So that's the conceptual idea for how this process works. But now let's look at the theoretical idea. So the point is this: is that when you have the tank of water, and you put the metal cylinder inside of it, so two things are happening. The metal is losing heat, so heat is going out of the metal, and at the same time that same heat is going into the water. So the same heat that leaves the metal is going to equal the heat that goes into the water. So that means that we're going to apply this equation here for both the metal and the water. So the heat that goes out of the metal is going to equal the heat that goes into the water. And if we just apply this equation for both the metal and the water, you'll have the mass of the metal multiplied by the specific heat of the metal, and then times the temperature of the metal initial minus the temperature final, because here both of them are going to wind up at the same final temperature, so T final, and that is going to equal now the heat that goes into the water. So that's going to be the mass of the water times the specific heat of the water, and then multiplied by the final temperature of the water minus the initial temperature of the water. So what this is good for is that the specific heat of water is known. So you can look up that value. So this equation is actually going to let us find the specific heat of the metal. So if you solve for the specific heat of the metal, here this is mass water. So the specific heat of the metal is going to equal, so if I do the algebra, mass water, C water, temperature final minus temperature water initial, and divided by mass metal times temperature metal initial and temperature final. So here, this is going to be the specific heat of the unknown metal. You're going to use this one to calculate the specific heat of the metal. So for the second part, it's going to be the same experiment, but now you're going to have it between an unknown liquid and water. So you're going to have some unknown liquid, which I'll call it LiQ, and you're going to have water. So the liquid, the unknown liquid, is going to be hot, So it's going to have a specific heat that we're going to want to calculate, C liquid, and it's going to have some initial temperature that's going to be hot, and you're going to have water. And what you'll do is similar to this one, just replace the metal here with the liquid. So you're just going to pour the hot liquid into the water, so that here the water is going to have some initial temperature T, well, the liquid is going to have some initial temperature T liquid initial, and then the water is going to have an initial temperature T water initial, and once you mix them, then the hot liquid is going to mix with the cold water, and eventually the temperature is going to stabilize to a final common temperature. And again, what you'll do is that you're going to measure the final common temperature, and you'll be able to calculate this equation here. So let's see how this is going to work again. So let's see. Once you mix them, this is the water, and then this is the hot liquid. So heat is going to leave the hot liquid, and that'll make that clear. So the heat is going to go out of the liquid, and at the same time that same heat is going to go into the cold water. So the heat that goes out of the hot liquid is going to go into the cold water. And from there, you'll get a similar equation to this one here. But really, so the point of this one is going to be to measure the specific heat of the unknown liquid. But it's going to have a similar formula. If you solve for this one, it's going to be the specific heat of the liquid is going to equal the mass of water multiplied by the specific heat for water multiplied by the final temperature that they both stabilize to, and minus the initial temperature of the water, and divided by the mass of the liquid, and then multiplied by the temperature, the initial temperature of the liquid, and then minus the final temperature. So it's the same formula as the first one. So really, part 1 and part 2 is the same experiment. The only difference is that for part 2 you're doing it with a liquid instead of with a solid. But it's the same basic steps that we've seen here with part 1. So this completes a theoretical explanation for the specific heat lab.